Hi, my name's Andrea, and I'm going to be talking about conditional hardness for sensitivity problems. This work is with Monica Hensinger, Stefan Newman, and Virginia Vasilevska-Williams. So, at high level, what we're going to do, we're going to be trying to get lower bounds for dynamic sensitivity in graphs. So, dynamic algorithms on graphs try and solve problems faster with preprocessing. We're making small changes over time, and they accumulate, and our graph changes. Sensitivity is going to limit what we're allowed to do in terms of these changes. So specifically, every time we make some small change, we're going to be forced to roll that back before we're allowed to make a new change. So we're going to stay in a graph that looks very similar to our original graph. And this is going to make the preprocessing more powerful and hopefully make algorithms faster. We're initiating the study of lower bounds for dynamic sensitivity. And for many of these things, we match the computation time or match the best known dynamic algorithms. And what this shows is that the hardness that comes in dynamic algorithms is difficult to overcome. It's not about changing your graph a lot, it's about the fact that these things just change very drastically. So dynamic algorithms, what's up with that? Well, we want to make updates and queries efficiently. These updates and queries are going to look like things like, I want to delete this edge, and then I'm going to ask something like, in this new graph, what's the diameter, or is it connected? Previously, there have been unconditional lower bounds from the cell probe model. They tend to be low, like if your data structure has a certain size, then your updates have to be like log n at most, at least. These sort of capture the time it takes to read in all the data. They don't capture the compute time. But some work has happened recently that has given much larger lower bounds by taking conjectures like the all-pair shortest paths conjecture or the strong exponential time hypothesis and saying, if you can do these dynamic computations efficiently, then you can compute these sort of normal RAM model things like all-pair shortest paths much faster. So for example, from strong exponential time hypothesis, you can show that diameter needs n squared time in order to be solved, or you can do stat much faster than you sort of expect. So that's neat. To some extent, people came up with sensitivity in response to that, but sensitivity came before those lower bounds. But it came out of the fact that, as was stated beautifully previously, sometimes it's really hard to come up with a dynamic algorithm that runs as fast as you want. And so you're like, well, maybe, because the word sensitivity will be confusing later, maybe I'm just doing emergency planning. Like maybe this road is gonna like explode, but only one road explodes at like a given time, and then we fix it. And so it's really, the road network of the US doesn't change too much. So what are we going to allow? We're going to allow, for the case of decremental 1 sensitivity, for example, we're going to allow you to delete one edge, roll that back, and delete one new edge. You're never in distance from the original graph that you preprocessed allowed to be farther than one edge deletion away. If you say decremental 2 sensitivity, you're allowed to delete 2 edges, and so forth. This is studied in various papers, and they get some nice upper bounds. But notably, they don't get nice upper bounds for everything. Here in this talk, I'm just going to be talking about 2 of our results. And both of them are conditional lower bounds coming from the all-pair shortest paths conjecture. We also get results from Seth and from an online matrix vector lower bound. But here right now, all we're going to say is we don't think we can solve all-pair shortest paths and enter the 2.9 time. It's just not a thing we believe in. It turns out that negative triangle is equivalent to this, where negative triangle is asking, in a graph, tell me if there are 3 points such that the sum of the weights on all their edges is negative. It might seem a little surprising that something that returns yes or no is as hard as something that is returning a giant n squared array, but turns out that's true. Pretty neat. So, what kinds of lower bounds can we get? So, one example is in weighted diameter, we can get an n squared lower bound from all pair shortest paths. An important thing to note is that Pre-processing time here is going to have to be limited. So we're going to say you're not allowed to have n cubed pre-processing time, you're only allowed to have n to the 2.99 pre-processing time, for example. This sort of makes sense because in general, for sensitivity problems, if I can solve the problem in some amount of time, I can certainly pre-process the entire graph and every possible query you're allowed to make in time n squared times whatever that is. Right? I delete the edge, I answer the question, and I solve that all in pre-processing. But if we're not allowing such excessive pre-processing, then it turns out with only n edge deletions and queries out of the diameter, we can detect whether or not there's a negative triangle in the original graph. This lower bound ends up being essentially tight given previous sensitivity results. And one of the reasons this is surprising is that here we get an essentially tight bound on how fast you can do diameter, but in our normal RAM model, diameter takes n cubed, all pair shortest paths takes n cubed, and we don't get it at lower bound from all pair shortest paths on diameter. So can some of these ideas be used there, or can we explain why? It can be used here, not there. That would be neat. So how does this sort of work? Well, I've got a tripartite graph in which I have a negative triangle, or not. And what I'm going to do is I'm going to sort of unroll it. So I'm going to take one of the sections and make two copies, put three sets of edges between these graphs, and then I'm going to add this horrible looking extra structure just to make sure that everything is really close to each other. So the diameter with this extra structure is going to be small. And what we're going to do is we're going to enforce that there's a matching between this subsection and this subsection and this subsection. And edge deletions on B are going to allow us to make just a pair of a node here and its corresponding copy to be far apart while everything else stays close. So we take a graph, we unroll it, we add some extra structure that has some nice properties, and it turns out that n edge deletions solves the problem. So if we can pre-process not too long and quickly answer queries, then we can solve all pair shortest paths by quickly solving negative triangle. Other kinds of things you can do. So what about shortest paths, right? We have all pair shortest paths. We should be able to get some lower bound on shortest paths. It turns out weighted directed shortest paths already has a lower bound of a similar form. If you allow less than n cubed preprocessing, you must take n squared time. This is called replacement paths and was sort of considered as a static problem where instead of imagining we're deleting edges from the graph, you imagine the query is packaged as a deletion and a request to return the shortest path at once. So a lower bound was found previously, and as a note, this means sensitivity problems can often be viewed instead as this sort of static problem. So what we do is we note that you can actually get this lower bound for the undirected case if you allow two edge deletions. So something that's surprising here is in the undirected case with one edge deletion, it's not this hard. With less than n cubed reprocessing, you can solve it faster than n squared. So this sort of shows you that these edge deletions do make things harder as you get more and more of them. In this case, the result really is tight. If you use Dijkstra, then without any preprocessing, you can get the n squared. And if you use Niradelli at all, with enough preprocessing, you can make very quick updates, like O of 1 updates. So, great, we're going to get n squared and n cubed lower bound again for the shortest path problem. So in conclusion, even in the sensitivity model, which seems like it's been constructed to make things easy on ourselves, we can still show hardness. And we often get matching upper and lower bounds. We can show that things are just as hard as recomputing from scratch, and other sorts of surprising results in the case where it seems like preprocessing should just be so powerful. Any questions?